Hello everybody, we're back to chapter 4. Just kind of remind you where we are. We have been looking at the formation of compounds, and we've been talking about ionic compounds. Now remember, we're dealing with ionic compounds, covalent compounds, and alloys. And an ionic compound is comprised of metals combined with nonmetals. And when we combine metals with nonmetals, we get the formation of ions, and the ions coalesce into the ionic solid. So remember, the ionic solid is made up of an array of positive and negative ions. And everything is interconnected through the ionic bond. So when we look at an ionic compound, and we talk about the formula of an ionic compound, we're going to talk about the empirical formula. Remember, the empirical formula is the smallest whole number ratio of ions, or smallest whole number ratio of atoms in the compound. Okay? So we're going to start off by talking about ionic compounds and empirical formulas. Now, let me scroll down here. Now, when we're looking at getting the empirical formula for an ionic compound, the formula is going to depend on the charge of the ions formed. Okay? So that the sum of the charges of the ions listed in the empirical formula of an ionic compound must add up to be 0. So as an example, if a sodium ion combines with an oxide ion in a 2-to-1 ratio, then it's going to take 2 sodiums to every 1 oxygen. Okay? And this we refer to as crisscross. Now, let's play with things for a little bit over here. I'm going to kind of do a little board work. All right. Now, if I had the metal magnesium, remember its Lewis dot symbol has 2 dots, and I wanted to combine it with oxygen. Oxygen has 6 dots. I know magnesium is a metal, and so it has a tendency to form positive ions. So magnesium is going to give up those 2 electrons and become 2+. Oxygen has 2 holes, so it wants to pick up 2 electrons. Okay? It wants to become, and I'm going to kind of star those in so you see they're different. It wants to become 2-. So 1 magnesium and 1 oxygen, magnesium loses 2, oxygen loses 2. So I have a magnesium 2+ and an oxygen that's 2-. Since they have the same magnitude of charge, they're just going to combine MgO. Okay, 1-to-1. Now, if I took that same magnesium and I want to combine it with fluorine, which has 7 electrons, fluorine only wants to pick up 1 electron to become there's the electron that it wants to pick up, the fluorine 1- ion, the fluoride ion, okay? Magnesium ion, fluoride ion. Now this time, if we look at it, magnesium 2+, fluoride 1-. The magnitude of the charges aren't the same. So in crisscross, we'd look at the magnitude of the charge here. It tells us how many of the fluoride ions I'll need. The magnitude of the charge here tells me how many of the magnesiums I'll need. So MgF2. Now, we don't have to go through this every time. By looking at where an element is on the periodic table, okay, we can pretty much figure out what the charge is. Or let's say we're given the charge. So let's say I have aluminum that's 3+, and I have oxygen, the oxide ion, at 2-, okay? The 2 as a charge of the oxygen tells me how many of the aluminums I need. The 3 as the charge of the aluminum tells me how many oxygens I'll need. So I'll get Al2O3. All right, that's crisscross. Now, let me throw in a poor metal, tin. Let's we have a tin ion 4+, so that's tin 4 ion. And we have a sulfide ion, S2-. Okay, if I do crisscross, I get SN2O4. But remember, for ionic compounds, we need to have the smallest whole number ratio. The 2 and the 4 have a common factor of 2. So I'd simplify this to SnO2. So that's the correct empirical formula. Okay? And now it's just a matter of practice. So let's do a couple more just to get some practice in. So if I were to take something like Fe3+, iron 3 ion, and I want to combine it with the oxide ion, which is 2-. If we do crisscross, okay, what we get is Fe2O3. Guys, this is rust. Okay, starting to get the feel for it. If I took silver 1+, and I combined it with phosphorus 3-, the phosphide ion, silver ion, phosphide ion, we should get Ag3P1. Okay, so that should be doable, right? Not too bad. Now, let's scroll on down here. So, we've done a few. There's a couple more that you can do. Let's think about naming ionic compounds made from monatomic ions. Monatomic, remember, means single atom ions. All you do is combine the name of the cation and the anion. Cation comes first, anion comes second, because in the formula of a compound, the element that's furthest to the left is always listed first. So when we're naming them, we name them in the order furthest to the left, further to the right. Okay? Now, let's look at some compounds and let's look at naming them. Okay? So notice you have transition metals, poor metals, because these metals, well, let's just look at naming them. Let's start out with some simple things. Okay, so if I went NaBr, this is a sodium ion. That's Na+. This is a bromide ion. So if I just combine those names together, I get sodium bromide. Okay? Now, if I had Ba, let's see, what barium compound do I want? Let's go BaF2. Okay, barium ion, so it's Ba2 plus. The fluoride ion is 1 minus. So I would have barium fluoride. Now guys, you don't have to go through this step, but I'm doing it just to kind of reinforce. You should be able to look at the periodic table for these two and figure out what their charge is, okay? Now, the other reason to look at this, because what if I gave you FeO? By looking at this, I know I have iron, I know I have oxygen, but I need to know the charges on the iron to be able to figure out what its name is going to be. So I know that the oxide ion is 2 minus. Since the iron and the oxygen are in a 1-to-1 ratio, I know the iron has to be 2 plus. So this is the iron 2 ion, and this is the oxide ion. So we would just name this iron 2 oxide. Okay? Now, what if we had NiCl3? Nickel is another transition metal. I know that chlorine ions are 1 minus, the chloride ion. So kind of doing crisscross in reverse, okay, think about it. That's an implied 1 there. This was 1 minus. So this tells me that this has to be 3 plus. So this is nickel 3 ion. So this is nickel 3 chloride. Okay, you got it? Let's try this guy. Now, this is the iodine ion. Okay, and this is silver. Silver only has 1 charge state, so there's no Roman numeral that goes with it. It's the silver ion, that's Ag1 plus, and this is I1 minus. So this is silver iodide. Now, what we can do in one direction, we also should be able to do in the other direction. So let's put up some names here and figure out formulas. So if I had calcium oxide, well, the symbol for calcium is Ca. It's in the second column on the periodic table, so I know it's 2 plus in charge. Oxide is the oxygen. Oxygen family always has a 2 minus charge. Notice they're the same magnitude of charge, so they just combine 1 to 1, CaO. Okay? Now, let's try another one. Let's look at lithium nitride. Lithium has a 1+ charge. It's in the very first family, the alkali family, alkali metals. The nitride, it's nitrogen, okay? It's going to have a 3- charge. So I get Li3N. If I have a transition metal, let's say like copper. So if I had copper 1 sulfide, the Roman numeral tells me the charge. So it's copper 1+. Okay, sulfide is in the same family, sulfur is in the same family as oxygen, so -2. So it'd be Cu2S. Okay? So those are things that we need to pay attention to. Just be calm and slow when you're doing it. All right. Now, because life can't be that simple, we need to talk about polyatomic ions. Okay? A polyatomic ion is an ion made out of 2 or more atoms that are covalently bonded to each other and as a unit carry a charge. So you can think about a polyatomic ion as being a molecule that's charged. All right, now let's look at the list of common polyatomic ions. Let's see if I've got them all. Yeah, that's all. Okay, guys, here's our list of common polyatomic ions. This is a chart in your textbook, okay? The good news here is that, believe it or not, this is a short list. The bad news is you've got to memorize these. You got to memorize name, formula, and charge, okay? Because these are common enough until you have to be able to recognize them when you see the formula. Now, most of these polyatomic ions are what we refer to as oxoanions. An anion, remember, is negatively charged. Notice most of these are negatively charged. The only one on this list that's not negatively charged is the ammonium ion. Okay, so most of these are anions. And they're called oxoanions because they contain oxygen, right, for the most part. So oxoanions. Now, there are some families of oxoanions. Notice here I have chlorine with 1 oxygen having a -1 charge, chlorine with 2 oxygens a -1 charge, chlorines with 3 oxygens a -1 charge, chlorines with 4 oxygens -1 charge. Okay? Because chlorine is the non-oxygen member of this polyatomic ion, the name of the ion is based on chlorine. So at the heart of it, okay, we see chloro, 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 chloro. Ite and ate as suffixes distinguish between high and low number of oxygens, and because there's 4 in this, we have a prefix of hypo and per. So the smallest number of oxygens is perchlorite. The next one up is just chlorite. Next one is chlorate, and then perchlorate. Okay? Notice with nitrogen combining with oxygen, there are only 2 options. So I have an ite and an ate ending. Now, the polyatomics, when it comes to figuring out formulas and naming them, we treat it just like any other ionic compound. So let's look at figuring out some formulas where we have polyatomics, and then we'll look at naming things. So if I had magnesium, which is 2+, and I want to combine it with a nitrate ion that's 1-, crisscross works here too. I'm going to have 2 of the nitrates and 1 of the magnesium. So I'm going to go Mg, and because there's 2 of the nitrates, I'm going to put it in brackets, write the NO3. That reinforces the fact that that's a unit. And then I'm going to put a subscript 2 down here. So it says I have 1 magnesium and 2 of these nitrate units. The name of this is magnesium nitrate. Actually, that should be a lowercase n. So magnesium nitrate. Okay, let's try some more. Okay, how about if I have sodium and a sulfate? The sulfate ion is 2-. Sodium is 1+. So if we do crisscross, I'm going to have 1 sulfate and 2 sodiums. So I get Na2. And since the sulfate, we only have 1 of them, we usually just write SO4. But you could also write Na2 parentheses SO4 if that helps reinforce for you that this is a polyatomic ion. And we just call this sodium sulfate. Okay. Now, let me show you, let's see. Let's say I have K 1+ and Cn 1-. Then these would combine KCN. Okay? Potassium cyanide. Now I want you to notice the IDE ending here. Cyanide, peroxide are the only 2 polyatomics that you've got that have an IDE ending. And that's because they're not oxoanions, okay? And that's why they get that IDE ending. The other one is the ammonium ion, and it's based off the common name of ammonia. All right, now, let's go backwards. I'm going to give you some names of some ionic compounds that contain polyatomics, and we're going to go back the other direction. So, let's see. Aluminum hypochlorite. Well, we know aluminum is a 3+. The hypochlorite, that ITE ending, screams I'm a polyatomic ion. It's ClO, and it has a charge of 1-. So if we do crisscross, I get Al, ClO, in parentheses, taken 3 times. Aluminum hypochlorite. If we had calcium, perchlorate, Calcium is 2+. Perchlorate, the ATE, screams I'm a polyatomic. It's Cl O4 1-. Okay, so I get Ca, ClO4 in parentheses, taken twice. All right? Now, what if I had iron 2 nitrite and iron 2 nitrate and iron 2 nitride? The names sound very similar, but they're different compounds. I have iron 2+, and the nitride ion is NO2 1-. So I get Fe NO2 in parentheses taken twice. Here again I have, in the iron 2 nitrate, I have iron 2+, and the nitrate is NO3 1-. So I have Fe NO3 in parentheses taken twice. And then down here, iron 2 nitride, iron is 2+. The nitride IDE ending is just a nitrogen with a 3- charge. So I get Fe3N2. So very similar sounding names, but very different formulas. Now guys, this just takes practice. I'm going to give you a sheet that's got all kinds of formulas for compounds and the names on them as a practice sheet. So you're going to get lots of practices with this. Don't panic, you got time to get it done. All right, let's scroll on down. Okay, we talked about that. Talked about that. We've done that. Now, the last thing that we have to deal with ionic compounds and naming is what are called hydrated ionic compounds. You know, in your day-to-day life, if you hydrate, you're drinking water, you're consuming water. So a hydrated ionic compound is an ionic compound that has water molecules associated with it. They're water molecules that squeeze in between the ions in the solid ionic compound. So it's an ionic compound that contains a specific number of water molecules associated with each formula unit, and it's called a hydrate. So Epsom salts is an example. Magnesium sulfate, notice the dot here, 7H2O. So for every magnesium sulfate formula unit, there are 7 water molecules in the crystal lattice hiding in and amongst the ions. Now, here, is cobalt chloride as its hydrate, which has 6 waters, and cobalt chloride without its waters, called the anhydrous version. Hydrated with, anhydrous without. Now, if we were going to name the anhydrous, cobalt is a transition metal. So the chlorines are 1- of each because of crisscross. I know that the cobalt is 2+, so it's cobalt 2 chloride. To name the hydrated compound, we're going to have to include the waters. So let's look at how we do this. when naming these compounds, okay, it's going to be the name of the salt, then a prefix with the number of water molecules, followed by the word hydrate. The prefixes that we're going to use for the number of water molecules are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. You got to memorize those. We're going to be using them again when we talk about naming covalent compounds. So you got some work cut out for you. Okay? So we're going to look at some examples of naming hydrates here. I'll just go ahead and roll that down. Technology and I are not getting along today. Okay, let's look at some examples. So let's look at the cobalt compound. Okay, if I just had this is cobalt 2 chloride. If I have CoCl2 with the associated water molecules, okay, we're going to get, come on, 6 water molecules. Yeah, just double checking. We call this cobalt 2 chloride. Hexahydrate. Okay. Let's look at this one. CuSO4 dot 5H2O. Well, this is the sulfate ion. It's 2 minus. So the copper there has to be 2 plus. So this is copper 2 sulfate. And there are 5 waters, so I go pentahydrate. Now, going the other direction, okay? Let's say I had barium chloride hexahydrate. Well, I know that barium is 2 plus and the chloride is 1 minus, so BaCl2. And then I have 6 waters because it's hexa. So I'll put a dot here, 6H2O. All right, and that is the end of naming. Now, I don't want to trivialize it. It takes a lot. A lot of people screw up the naming on this exam. So start early, do a little bit every day practicing, and you'll make it. Okay? Don't get overwhelmed by it. You can do it. All right. Now let's talk about the formulas. Well, the properties of an ionic compound. The physical properties of an ionic compound reflect the strength and the properties of the ionic bond. Because remember, in a solid ionic compound, all of the ions in one solid chunk are interconnected by the ionic bond. It extends throughout. So ionic compounds have a tendency to have very high melting points and very high boiling points. They won't conduct electricity in the solid phase. They won't conduct heat in the solid phase. They will conduct electricity in the liquid/molten phase. We usually refer to the liquid phase of an ionic compound as molten because we have to get it so hot to get it to liquefy. So it will conduct in the liquid phase. And it will conduct if we dissolve it in water. Okay? The